Okay, so hi everyone. I'm Dean. I'm a fourth year PhD student working with Robin and also Robert Platt in the robotics department. So today I'm very happy to talk about some of the applications of using equivariant learning in robotic manipulation. So I guess we have been hearing the math from Robin all semester long, and
everyone else.
yeah, everyone else. So yeah, I assure you that this lecture will not be that math heavy. So we will be focusing on some of the, real world applications of, how can we use the stuff we learned from this course in realistic problems. So I work in robot learning. So recently there have been a lot of success in using machine learning methods to solve robotic problems. On the left, there's a example in solving grasping using machine learning methods. So you can see that the arm is, trying to pick up the objects in a tray, and then there will be a camera that records the images while the robot is moving to grasp the stuff, and then try to generate a policy based on the input image. On the right, there's a reinforcement learning application in local motion where the robot is trying to learn how to walk from real world experiences directly. So they have been, pretty successful in using machine learning techniques in robotics. But one of the main problem is that machine learning algorithms are always data hungry. So in the grasping demo we showed were cool, but in fact, it takes the folks from Google 4 months to collect 800 robot hour data from 7 robots. So that's really a huge amount of data. So imagine for a standard research lab like us, it's really hard to do that because we don't really have that many robots, we don't really have that many software engineers to make that possible. So one alternative way of solving the problem is to train the policy in simulation, and then we can deploy the trained policy in simulation in the real world. But still, since we are in robotics, we need to simulate the physical context. We need to simulate all of the transitions that when the robot is exploring in the world. So it's still not fast enough. Also, we will face the so-called same to real gap because the physics in the simulator will not be perfectly matching the physics in the real world. So you need to somehow fill that gap, or you need to do some adaptation in the real world. So the question here is, how can we improve the learning efficiency? How can we make our learning algorithms more efficient so that we can learn a policy within a reasonable amount of time in the real world? So how does robotics normally solve problems? I think one of the main strategy is that we try to leverage structures of the real world. We want to find the physical property, we want to find the geometric property of the task we are solving, and then we find the proper architectures for solving those problems. I think this greatly aligns with what we have been learning in this course, right? So in geometric machine learning, we try to identify some geometric property of our task, of our machine learning task, and then we find the best equivariant learning algorithm to solve it. So, the answer of this question, are there any easily accessible structuring manipulation that can help? The answer is definitely symmetries, what we have been learning in this course. So how does symmetries exist in robotic tasks? So here I have a very abstract example. So imagine you are a robot, and then you are facing a table with 3 objects on it. So now you want to pick up the green trapdoid, right? So the black thing is the robot gripper. So you can pick up the trapdoid this way, right? Now imagine there's a rotation on the table, on the table has been rotated. Now if you execute the previous grasp but rotate it, you still have a good grasp, right? So this is essentially the same grasp, but both of the grasp and the thing in front of you are rotated. So those should be considered as the same thing, but in standard machine learning algorithms, as we know, they always treat those 2 different type of inputs as 2 different training samples, and they need to learn from both of them separately. So our goal here is to design algorithms that can automatically generalize over symmetries. So today, I will talk about a list of works that we have been developing in the past, I guess, 2 or 3 years. I'm not sure if I can go through all of them, but I'm just listing all of the stuff here. So first, I'm gonna talk about group environment MDP, which is a theoretical grounding of like how can we apply equivariant learning in robotic manipulation. And then I'm gonna talk about 2 or 3 different like directions. So that in the first one, I'm gonna talk about how we can use equivariant policy learning in continuous control, right? So I will explain what is continuous control in a second. And then in the second part, I'm gonna talk about equivariant learning in spatial action space. This is a different problem simulation as the first one, but we can apply similar strategies in both of the tasks. And in the end, I'm gonna talk about how do we handle latent symmetry, because in real world tasks, this symmetry are not always presented like perfectly in our tasks. And sometimes we need to handle this sort of like latent or implicit symmetry in our task. Okay, so first, group environment MDP. So to talk about group environment MDP, I guess I need to give a brief background introduction of Markov decision process MDP. I guess some of you might be familiar with that, but I just want to make sure that we're on the same page. So a Markov decision process is a 4 tuple, includes S, which is a set of all possible states, and A is a set of all possible actions we can take as a as a robot. And then we have a transition function T, which is a function of the current state, the action, and the next state. It tells us the probability of reaching the state S prime after taking action A at state S. And then we also have a reward function, which is a function of state action that tells us how good it is for taking the action A at state S. So once we formulate our problem using an MDP, we can try to solve it using reinforcement learning. I guess, a lot of you might know AlphaGo or, related algorithms that's basically built on reinforcement learning. You have an agent that interacts with the environment. The agent will take an action in the environment and receive the next state and the reward for the action. And then you keep those data in your replay buffer, and then you train from your own experiences. And then this is reinforcement. So
are you going to give an example?
Yeah. So for example, in robotics, right, like the state can be a lot of different stuff, but maybe just imagine like the grasping example that I showed before. The state can actually just be an image of your bin, like the objects in your bin, or maybe the image will also contain the robot, so that the agent can see where itself is located. And then the action can be, for example, the XY position of the grasp, or including the top-down orientation of the grasp, or if you want to do the full 6-stop or the full SC3 grasp, you can also include the autoplane orientation, like the SO3 rotation as well. And then the transition probability and reward function can be just defined properly. For example, the reward can just be +1 if you successfully take out the object, and then 0 otherwise. Okay, so this is MDP, and we can actually.
I have a question.
Yeah, please.
So going back to the previous example.
Yeah.
So just to make sure I have this straight. So in the example of like your robot with a bin of objects.
Yeah.
So states were just all the objects in the bin.
Yeah.
Okay. So usually your set of all possible actions is much larger than your set of possible states. So.
I think that depends on how you define the size. For example, like when we are in image space, technically the state space is infinite, because we can have arbitrary images for the agent, and the set of actions might just be like maybe constrained by your workspace. For example, you can only go like 50 centimeters along X and Y direction, and then Z also 50. Yeah, I think it's a little bit hard to compare like the size of the state and action space.
But S here should be finite, because you want to be able to segment your relevant states in the image, right?
Oh, that's a good point. So the S can be both finite or infinite. So normally when we think about like using ground truth state, sometimes we think about the state space as a finite space, and then in that case we can try to use some so-called tabular methods for solving the problem, because you can list all of the states and then you can basically save all of the outcome of in each state in a table. But sometimes we will also consider like infinite state space. For example, the image space is infinite because we want to, we want our method to generalize to unseen states as well. In that case, that would be like an infinite state space. So in this talk, I will be focusing on infinite state space. Mostly the state space will be images.
I think intuitively, I think of the state space as bigger than the action space, because like the state space, like a state needs to be all the information I know about the environment I'm interacting with. Right? The location of all the stuff, the location of the arm, like everything, right? Whereas the action just describes the parts I can manipulate directly, right? So like in this robotic setting, the state needs to describe all the stuff that's within and the arm, whereas the action is just how you're going to move the arm. Because you can't like move the grapes. You can just move the arm, right?
Yeah, I guess I was thinking more of the action as like the act of on the state. To do on the state.
Yeah.
What you're saying.
Oh yeah, I guess that's a good point. Yeah, there's like a subtlety of the definition about whether.
Yeah, the action will not like directly acting on the state, for example, like by a linear matrix modification or something like that, but it's more like in the environment, the environment based on the current state and the action that is taking, the environment will generate the next state. So this is not necessarily like a like a group action.
Sure.
Yeah.
Yeah, you could say like the product space of states and actions is larger than the state space.
Yeah. All right, cool. So now let's look at our actual problem in robotic manipulation. So a lot of the robotic manipulation tasks can be formulated as in the SC2 space. For example, here we have a block pushing task. The goal for the robot is to find the yellow block and then push it. So we can maybe define the state as the state of the gripper, which contains the XY theta, which theta is the top-down orientation of the gripper. And then the state will also contain the XY theta, like the IC2 poles of the block. So I said that we'll be using images as they say, but right now let's just think about it like abstractly, like just use the ground truth state. For example, the IC2 poles of the state and the IC2 poles of the gripper and the block as the state. And then our action can also be defined in the space of IC2, where it's just gonna be IC2 vector, right? We're gonna know like how we want to move the gripper along the X direction, along the Y direction, and then how we want to rotate our gripper with respect to the current orientation. So both the state and action can be defined in the space of IC2. So in that scenario,
Just to remind, so
Yeah.
SE2, so that's the position
Yeah.
and the orientation.
right, top-down orientation.
Okay.
Yes. In that scenario, there might be some SO2 equivariance in our task. How come? So for example, we are in the state S, and then we execute a pushing action towards the bottom of the workspace, right? And then we end up with the new state S prime. Now let's imagine there's a 90-degree rotation applied to the state. That means both the gripper and the objects are rotated in the state. So we end up with a new state GS. And then we apply a rotated action as well. Before we were pushing to the bottom. So here the rotated pushing action will push to the right. And then we end up with a new state as double prime. So what we can see is that this S double prime is actually a rotated version of the state S prime. So we can also write it in terms of G of S prime, right? So mathematically, this can be formulated as an invariant property in the transition function. So recall that the transition function represents the probability of reaching the state S prime when taking the action A at state S. So this action can be written as an SO2 invariant function. So that means if we apply the same rotation to the current state, the action we are taking, and the next state, the transition probability will not change. So there are some implicit assumptions here. For example, the tabletop has the same friction across the workspace. Otherwise, when you rotate, you might end up with a different area with different friction coefficient, then your pushing action might have different results. But let's just assume that the entire workspace have like similar or the same physical properties. Then we can write the transition function as an SO2 invariant function. Yes, please.
I have two questions.
Yeah.
Okay, first of all, this picture you drew.
Yeah.
Looks like an equivariant thing.
Uh,
And it says equivariance, but then you have said it looks like you wrote invariance. So that's my first question.
yeah. So well, I guess that depends on how you formulate the question because like here is an invariant function, right? But if you write the transition function in terms of the current state and action,
Yeah.
and then the output of the transition function is the next state, then the transition function is an equivariant function, right? I guess it's invariant here because we are encoding all of the components in the input of the action, input of the function. Yeah.
All right. I have another question.
Yes, please.
You said you wanted to ignore like different frictions.
Yeah.
That sounds fun, like interesting.
That sounds interesting.
Yeah.
Like
that sounds like an interesting problem to study.
Oh,
Like it would be equivariant, but there might be different frictions.
Yeah.
That sounds like really. Can we make that environment?
Like an environment with different frictions in different. Yeah, we can.
All right. Let's study that.
Yeah. So. Yeah, I guess the short answer to that question is, as long as those areas are visible in TTR agents, then we will have, actions in equivariant. Yeah, yeah, we will not go to detailing.
Okay.
But yeah, we can definitely. Yeah, that is indeed an interesting direction of research because that will release some of the assumptions that we are making in the current approach. Yeah. All right, so we can also write the reward function as a invariant function because our goal might be invariant to wherever the object is located. For example, in the block pushing task, we might just want to push the block. We don't really care where we want to push the block to. Or like a more intuitive example will be for grasping, right? We just want to pick up the object. It doesn't really matter where the object is. So I want to pick up the bottle, right? Like it doesn't really matter if the bottle is on the top, it's on the bottom right of the table or it's on the top right of the table. I just want to pick it up. So the reward function is always like invariant to SO2 rotations. So with that, we define group invariant MDP as an MDP that satisfies the two invariant properties in the transition and reward functions. So we found out that given any group invariant MDP, we can prove that its optimal solutions are also group equivariant. In particular, the optimal Q function is going to be group invariant. So a Q function represents the quality of taking taking action A at a given state S. So it's similar as the reward function, but the reward function might be sparse. So imagine like you are just trying to pick up the object, right? So you might only get the reward at the last action. But in order to let your agent know how good action is before like the last step, you need to kind of like back propagate your reward to all of the previous states. So basically, I just think of it as a quality, like a more dense quality than the reward function. So the optimal Q function is going to be group invariant. That means if you rotate your state and action at the same time, the quality of your action will not change. And
can I just for the Q function? So you're saying the difference between the reward and the Q function is the reward is very immediate. I only get the reward when I do something good. Whereas the Q function is like encoding long term. Yeah. So it's like it's a good thing if I'm headed towards getting some reward.
Exactly. Yeah. And then the optimal policy function is going to be group equivariant. So a policy function is a function from state space to action space. So you take input of a state and it generates an action. So that function, the optimal policy function is going to be group equivariant. So I will talk about both of them in detail in the next slides. So first slide look at the equivariant policy function, right? So what I mean by equivariant is that when the state is rotated, the output action should be rotated accordingly, right? So that means if we rotate the state and then send the rotated state to the optimal policy function, we should get the same action as sending the unrotated state to the optimal policy function and then rotate the optimal action. So this is an equivariant property in the optimal policy function. And then for the environment, so for the environment property in the Q function, that means if we rotate the input state and action at the same time, the output Q value from the optimal Q function should not change. So that is like the equivariant property in the optimal solutions of an MDP when we have a group environment MDP. So any question about this? Yes, please.
Sorry, I think I'm just confused. So
Yeah.
your SE2 equivariant regardless of like your choice of frame.
Yeah. You can simplify that way. Yeah.
But I feel like rigid body motion in general is not equivariant with the choice of frame. Like that's what I'm struggling.
Yeah, so okay, so I think you're right. So if you think about, like, for example, the kinematic constraint of the robot, right? So maybe if I rotate my my coordinate frame or rotate my workspace, some of the previously reachable state might not be reachable anymore. So that is true. So that's actually something that we are currently trying to solve. But in this line of work, I'm just gonna assume that we are not constrained by such like kinematic constraints.
Okay.
Yeah, just assume that.
It was, yeah, I mean, like, I mean, with rigid body motion, you've got like cross products floating around, right? And those are all dependent on your choice of basis, right? So yeah, I was confused as to like how, like, for example, if you're looking at the torque you apply to something, that's dependent on your choice of basis.
I see.
When you change it, like I feel like rigid body motion, but that's one of the struggles in rigid body motion, that's your choice of basis.
Not sure if I follow.
Yeah, so the torque.
Well, here your action space is just X, Y, theta.
Yeah.
So there's no. choice.
XY theta.
Like,
Yeah, of the
Oh,
of the gripper. Of the
They're
gripper.
saying like, even though they like show physical robots there, the like, they've like actually abstracted it away.
Yeah.
So they just have like a disembodied gripper arm, and the actual like instructions they give to the gripper arm are like, be here,
Yeah.
be there,
Okay.
open, close. And then that's some robot some company made, and they pass those instructions and they let the software of the robot actually figure out what quirks to apply to the
Okay.
motors.
Yeah,
No, this is cool. I've never.
yeah, but I believe that, finding the equivariance in, like, kinematics or rigid bodies, that would be like a very, very cool application of equivariant models, but we haven't explored that yet. I think, yeah, maybe Dinfeng is doing that. Yeah. Okay. Right. So, yeah, so we talk about like group environment DP, and then I'm gonna talk about the first application of it in the continuous control. So the continuous control is actually just means that we want to control the delta motion of our gripper. So at each time step, we want to tell the robot the relative motion with respect to the current position. So this is, it's not a very precise definition, but let's just think about it that way. So we already talked about the equivariant property in the optimal policy function, and then we talk about the environment property in the optimal Q function. So now our goal is to enforce such properties inside networks. So to do that, we will first need to create a good representation of state action that we can use in equivariant network. So for the state, I will define the state as a top-down image centered with respect to the gripper. So in that way, we can encode the rotation of the state as the rotation of the action. And then I will define the action as the relative movement of the gripper in the XYZ direction and also the top-down rotation. So if we define it that way, when we say we want to rotate an action, that actually means we want to rotate the XY component of the action by a 2x2 position matrix. And then we will leave the other action components unchanged. For example, your Z action should not be changed by an SO2 action, right? And also like your top-down rotation will also not be affected because when you rotate the state, your current gripper rotation is rotated accordingly. So the change of rotation should not be affected when you are rotating your entire state. So I guess maybe you can think about how we're gonna actually do it, right? If we want to use an E2C in or like the steerable convolutional networks, we will be just constraining the XY as a row one representation of SO2, and then we will using the trivial representation for the Z and theta action. Yeah, and then with those definitions, we introduced the first learning algorithm, Equivariant SAC. So SAC stands for soft actor graded. Is reinforcement learning model that will maintain an actor and a credit. So an actor is a mapping from the state to action. It's basically trying to model the policy function. And the credit is a mapping from state cross action to real number. That's basically representing the Q function. So we can then just constrain the Q network as an invariant network and constrain the policy network as an equivariant network. And then we just implement that using the steerable CNN. So as I said before, for the representation types of the invariant network, equivariant network, for the image, we will just use trivial representation of the image. That means like when you rotate the image, you don't expect the pixel value of the image to change, right? And then for the output of the policy function, we will use row 1 for the XY action, and then we will use row 0, the trivial, for all of the other action components. And then similarly goes to the invariant Q network. So for the input of the Q network, there are 2 separate inputs. For the state is again a trivial image representation, and then for the action is again like the same representation that's being used for the equivariant policy network. So any question about this method? Okay, cool. Yes.
Why do you use just rotations, not reflections?
That's a good question. And then we used reflections. I was not talking about reflection because it's easier to introduce a method with just rotation only. But in fact, like all of those properties can also be applied to reflection. And there's also interesting about reflection where if you just do rotation, your relative change of top-down rotation should not be changed by the rotation of the state, right? So like if I'm want to grab the bottle, I need to rotate my gripper clockwise a little bit. And if I rotate the bottle and my gripper at the same time, I should also rotate clockwise a little bit. But if you consider reflection, that's actually gonna negate your delta theta action. Like if you reflect the state of the bottle and the gripper, like the clockwise, it's actually gonna change into like a counterclockwise, and then you need to address that property in the framework. But yeah, we can actually include the reflection in the model. Yeah. Yes.
So network structure here is CN or
It's in.
are you controlling joint angle or joint
No, I'm not controlling joint angle. I'm just control. The action is the delta of the end effector poles, and then the joint is controlled by the the UR5 robot or whatever robot we are using. Yeah.
If you consider about use the joint encoder and joint angle velocity as your obstruction space, then also became a joint encoder.
I didn't think about that, but I did think about another thing, which is like, for example, if I want to control the joint space directly, right? So the joint space doesn't have explicit equivariant properties. We cannot define, well, at least, as I was thinking about it, I think it's hard to define the group action on the joint space, but we can define the group action on the end effector space. But there's a mapping between the joint space and end effector space, right? We can use forward kinematic and inverse kinematic to map those two to each other. And, can we somehow turn the group action on the end effector space into some implicit action on the joint space, by incorporating the group action with, I guess, conjugating the group action with the inverse kinematic. Yeah, I just thought about it for a second, but I didn't like really look into it. Yeah. Okay, so yeah, so we have this network, or we have this method, and it worked out great. So here I have a comparison of the conventional stack algorithm versus our equivariant stack algorithm. So we can see that the equivariant stack algorithm is learning to solve this drawer opening task much faster than the conventional stack algorithm. On the left side, I have the number of training step, number of episodes it's experiencing, and then the success rate for the previous 20 episodes. This is a bit small, but here the equivariant stack can completely solve the task with a 100% success rate after 1,200 training steps. But after the same amount of training steps, the conventional stack can only reach a 20% success rate. So more quantitatively, here I show the compare.
How do you initialize the policy?
How do I initialize the policy?
Yeah, it's random.
Oh yeah, the policy is initialized randomly, but I will provide the algorithm with some expert demonstrations. Like there will be some expert transition that shows the robot how to successfully open the gripper. Open the drawer. And then those transitions are pre-populated in the buffer, and then the agent will start learning from those demonstrations and also learning from its own experiences. Yeah, but it's the same. Like I'm not only giving the explanation for my method, I'm giving it for all of the, all of the methods.
Okay.
Yeah.
So that's how it succeeds, because it's kind of like twitching around helplessly. And then every once in a while it kind of like actually does something useful.
Yeah. That's because we can see that when so every time we initialize the state, like the drawer might be located in different locations, right? So the equivariant policy can actually automatically generalize to all of the rotated drawers. But for the standard stack algorithm, we need to learn how to solve the task in different orientations one by one. So that's why like we have this so dramatic improvements. Yeah. Okay, so we did some experiments in different environments. Here I have object picking where for each episode, the robot need to pick out some object, and then while pulling, the robot need to pull one of the two blocks so that they are making contact with each other. And then drawer opening is like just opening the drawer. So here on the bottom, I have the so-called learning curves, where the x-axis is the number of training steps, and then the y-axis is the evaluation performance. So for example, every 500 training steps, I will pause the training and then evaluate the learned policy to see how it works out. And then the blue line is our method, the equivariant stack, and then all of the other colors are the state-of-the-art baselines, but was not using equivariant networks. Yes, please.
So when you evaluate though, like how are you changing the environment?
The environments are always randomly initialized. For example, in the drawer opening, the robot will always be at a fixed position, but the drawer will be in a random position. Similarly goes to all of the other environment, like the objects will be randomly placed in the environment. Yeah, so we can see that the only baseline that works a little bit is the yellow one, where it can solve this block pulling task. But in the other two environments, none of the baseline can solve the task, but we can learn to solve it. We've seen like 2,500 training staff, like it's a very significant improvement than baseline. Yes.
So if every training step is a new random placement of the drawer, right?
Yeah.
And then you're doing the same thing when you evaluate every end.
Yeah.
Like,
Yeah.
So what does overfitting look like? Or is that even something that can happen?
Overfitting?
Yeah. Is that
You mean like
is there an instance where like it could train properly, but then when you go to evaluate it, it just fails? So what would that look like? Maybe if you change like the handle shape, I don't know.
Yeah, that's possible. I actually, in my experiments, I use the same environment for training and evaluation. So I didn't really test like what will happen if we change the handle like size or something. But I think that is more like a general problem for machine learning or for convolutional networks, right? So how do we generalize to the unseen states? But here, I guess we are more focusing on how do we generalize to the rotated versions of the same state, right? So, for example, for the CNN, you might see how to act with certain drawer orientations. But during testing, when it sees a different drawer orientation, it doesn't know how to talk. Oh, actually, I think I did have one experiment in one of my papers, but I forgot which one. So during training, I only initialized the objects within 0 to pi rotation. But during evaluation, the environments are initialized from 0 to 2 pi. So in that case, like I think, if I remember correctly, like a lot of baselines have very bad performance. Like at most they can learn 50%, but the Equivariant method can actually generalize to the other half of the circle. Yeah.
But I mean,
Can I ask about the first?
go ahead.
Yes.
About the object picking, I mean, the difference is so huge. So related to the previous question, first of all, is like, do they have good reward? The baseline methods, do they achieve non-zero reward in the training, during training, but not on the eval?
I think
Or are they zero?
it's also 0 during training. Yeah, it was just all bad all the way.
It
So
doesn't look that hard.
well,
No,
I mean, are there other baselines? Like, is this a task that's sort of previously not well solved, or like, how come these are?
yeah, that's
So
so I think there are a couple of perspectives why this task is hard. So first, recall that we are in this so-called closed loop control, right? So at each time step, we are controlling relatively, how do we want to move the gripper with respect to the current pulse. So I think for the object picking, it will require like around 8 or 9 steps for solving it. So the reward is sparse. You only get the reward when you pick up the object. So the reward needs to be back propagated to all of the previous 7 or 8 states while you are training. So I think that will dramatically like exponentially increase the sample efficiency difference, right? Because at each back propagation, you will be more efficient, and you're just gonna be like a lot more efficient if you have more steps in your training. The second perspective of why this is challenging is that we in our action space. So I show that I defined action space as x, y, delta x, delta y, delta z, delta theta, right? Actually, there's a fifth one I ignored in the slide. I was also controlling the gripper open width. So this is a 5-dimensional action space.
Yeah.
So this task was actually solved before in a 4-degree of freedom action space. So some people solved it when he was just controlling the delta x, y, z, and open width. But here we included the top-down rotation. So every new action dimension you include in your action space is going to dramatically increase your learning complexity. So that's the second reason why this is so challenging. And I guess a third part is that we are actually only training it to 20K training steps. So that's not a huge number in reinforcement learning. So if you think about like how AlphaGo was trained, it's just millions of, hundreds of millions of training steps.
Right.
Yeah, but here, we are only training with a small amount of training steps.
Is this state-of-the-art performance for this task, for those degrees of freedom, for that number of training steps?
Yeah, I think so. Yeah. So I think before us, work method is one of the state of the art.
Yeah.
And I think, we beat them pretty well. Yeah. But I have to say that, our method is more like constrained. We are assuming that the reward function is environment, the transition function is environment, and, we will need this top-down image so that we can use the Equivariant network. But the baselines, even though like here, they are not like doing very well, but, they are more like general, like it doesn't need to have those constraints. Yeah.
Yeah, a related question, would the differences change if you sort of chose a schedule for how to sample training episodes? So that, for example, for yours, you could sort of have the optimal subset of episodes that's just a minimal kind of basis of things, and you could maybe saturate at really, really early. Or if you chose them to be, maybe easier for the baseline methods, maybe they can start to learn sooner rather than having this difficulty. Like if they keep receiving the same episode over and over, eventually they can solve at least that one episode, or you know.
Sorry,
So do you expect this gap really depends on that like sort of randomness or not really?
Sorry, I don't quite follow. Like when you say schedule, you mean like the scheduling of how we see the expert demonstrations, or what is the scheduling that?
Not the expert part, but just like the kind of random. Sorry, schedule is maybe not the right word, but just the randomness of like the training episodes. So each time you reinitialize the object or whatever, and you.
I see. Yeah, that's a good question. I think this is referred to as curriculum learning, where you can, set up the training process so that at the first stage of training, you always show some of the easy task, or you always show the same like setup for the agent to solve. And then once you solve the first stage, you include some randomness so that the agent will adapt to that randomness. So yeah, there is actually works that does this curriculum learning. But here I'm not like, yeah, I didn't consider that. I was just keeping the same like learning scheme for all of the methods. But I believe like the side is correct. Like, if we include some curriculum learning here, the baseline might be better. Yes.
Okay, thanks.
Yeah, and I also think the same benefit will also goes to our method. So like maybe you can learn even faster. Yeah.
That's another topic.
Yeah.
How do you do equivariant curriculum learning?
Yeah. You can separate the curriculum in an equivariant way, or like, well, I guess.
We don't need to solve it now.
Yeah.
I've never seen this work, so.
Yeah, well, I guess
It's redundancy.
the fundamental domain, like, all of the things in the fundamental domain should be separated into different curriculums. But anyway, yeah, that's a cool topic. Yeah, and we also tried to solve some more challenging tasks. Like here we have block stacking, right? The robot need to stack 2 blocks on top of each other, and then have house building, similar to block stacking, but it's stacking 2 different type of objects. And then corner picking, the robot need to nudge the object out from a corner and then pick it up. So those are more challenging than what we have seen in the previous slide. So since they're more challenging, I actually included some demonstration loss. So there will be an extra loss term that will guide the actor or the policy network to act more like the demonstration. So that's why it's called SAC from demonstration SCCFD instead of SAC. But again, here, like I'm including the demonstration loss to all of the methods, and none of the baselines can actually solve those more challenging tasks, and we are the only one that can solve it. So this is great, but we are still learning in simulation. But we can see that we can actually solve those tasks within very small amount of training steps, especially in the previous slide. We can see that we are solving them. We see maybe 1,000 training steps or so. So that make us saw that maybe we can start learning directly in the real world. So that's what we did in the next project. So here we did on-robot learning, where we have just a physical robot exploring around in the environment, and then we learn from its own experience. There was no pre-training, no simulation at all in this project. So here we consider 4 different environments: block picking, which is same as before, just pick up the block; block pushing, where the robot need to push the block to some virtual goal. The virtual goal is going to be directly drawn in the image, so that it's not visible to the human, but it's going to be visible for the robot. And then we have clutter grasping, where there are some objects in the clutter, and then the robot need to pick up one of the objects. And then blocking ball is a pick-place task, where the robot need to pick up the block and then drop it inside the ball. So in those 4 environments, we can actually solve the first 3 within 1 hour. So that's like a very fast learning speed. If you think back of the grasping project I showed on the first slide, we are 800 hours that required. And then for the blocking ball, it actually took us 2 hours and 40 minutes, because like resetting the environment is very like time consuming, right? Like we are doing reinforcement learning. So yes. Oh, okay. So we are doing reinforcement learning, so we need to reset the environment every episode. So if you imagine blocking ball, you actually need to like reset 2 objects instead of 1. So it's actually taking more time there. And during evaluation, in all of the four environments, we can achieve more than 90% success rate. And then we also compared with like the firm baseline, which is the yellow one that in the previous slide, which was the one of the best. And we still outperform it significantly in the real world. So basically solving the task within 2,000 training sets or 4,000 training sets.
So most of the actual like experimental time is training baselines, or did firm give you these results? These look like you reproduced the results.
Sorry. Oh, yeah, I reproduced it because in the firm paper, their action space didn't include the rotation. So in order to make it work in our environments, I need to rerun. Also, this is reinforcement learning, right? So we always need to rerun the method so that it's learning in our environments.
Right.
Yeah, we cannot just use their data directly because the environments are slightly different. Yeah, like running the baseline is definitely more time consuming than our method because it's just gonna make more failures and then more manual reset is required.
But you made it easier for yourself by just training it for the same amount of time and then reporting. Like you don't know how many hours it takes firm to achieve.
I didn't record it, but it's slightly longer, but not too bad because each time step is actually gonna be similar. Yeah. Yes, please.
If you use others method like multi-equivariant statistics, can those methods achieve the performance like yours?
No. The non-equivariant stack will be much worse. So if we refer back to the simulation, here the green line is actually the same as the blue line, except that it's not using equivariant network.
Yeah. So you train them in 20,000 steps. If you train them in 200,000 steps or more.
Yeah, I think eventually it's possible that they can learn, but it's just gonna take longer. Yeah, okay. But it's also possible that it won't learn. It's kind of hard to say, like, because for reinforcement learning to work, right? So the agent needs to see some of the positive results so that you can backpropagate those rewards. So yeah, I guess for this task, maybe you can learn because you're ready to see some of the success. But for the others, like if it's always zero, it's gonna be tricky for any algorithm to learn. I guess if I include more demonstration, those baselines can work.
There's no like theoretical result that like at infinite time it'll eventually converge.
That I'm not sure. I think maybe, but yeah.
That's true for like tabular.
Yeah, tabular RL, yes.
But not necessarily for DeFi.
Yeah, I think empirically it's hard to say. Yeah. All right. Yes.
So all those time are based on would be some basic demonstration.
Yeah, I gave 20 demonstrations.
Then estimation if you gave no demonstration, let's see, it's for.
Oh yeah, that's a good point. So if you don't give any demonstration at all, it will be very challenging, even for our method. Yeah, because of the reasons that we were talking before, like for example, the long time horizon or the sparse reward or the large action space. Yeah, it's gonna be challenging for our method as well. But I kind of remember that for some of the tasks, like for example, the block picking or pushing, the robot can still solve it. But it's just gonna take much longer than 2,000 4,000 training steps. Yeah.
What about one demonstration?
One demonstration. I don't think I tested it, but it should work for some of the environments. Yeah, we do have one demonstration experiments in other papers.
Yeah.
Yeah. Okay, so I guess we should take a break now because that's the time we're normally take. Yeah.
Is now a good time?
Yeah, that's a good
Okay.
time.
Cool. We usually bring snacks.
What? I don't know. I don't remember that.
Some intermediate report.
We're on track to get through everything we planned.
No. I will skip some of the tables, I think.
There's a makeup day, so we could add a day to report.
The makeup day for what? For the university?
There's like a day where the room is reserved, like an extra day.
Oh, I see.
But I think technically you need to have like 1 day.
Really?
Yeah. I mean, I don't know if it's reserved for. Like for
Don't they
graduate classes,
transition to-
or for graduate classes, it goes through. Because there's no exam period. for graduate classes.
Oh, really? Oh,
Yeah. Actually, technically, they're supposed to do that.
oh, I didn't know that. So
Oh,
I
yeah,
should,
no, it's.
I should cancel the final exam.
Yeah, if there is a final exam, it has to happen like on the last day of class.
And so the registrar will reserve the room through the exam period and schedule.
I assume so. I mean, you can check 25 line. Oh, but
Yeah.
How do you integrate your demonstration into the?
How do I?
Yeah, like
Oh,
learn, so does your reward is the distance between your action and the demonstration?
no, the reward is not the distance. The reward is just a binary reward, like you got a +1 when finishing a task. But the extra loss term, when I was using, for example, the aside from demonstration method, I included the extra loss term. In the loss term, the loss is actually the L2 distance between the current actor output to the expert action. So this extra loss is only applied to expert demonstration. So when you sample expert demonstration, you know what the expert should perform, right? That's the action in your transition, and then you include that extra loss term. But for self-generated transitions, I don't include that. Yeah.
So all the method you try was model 3 or?
Yeah.
Have you tried model 3?
Not really, but I think Nathan tried it. He did some work in Equivariant value iteration network. I think that's more like a model based, but I think it should be able to apply to model based method, because the same assumption can be applied there, like the transition environments or reward environments, and then you can just incorporate the symmetries in your planning or in your model. Yeah. Okay, cool. So I will continue. So I wanted to talk about this work, but I think I will skip it because of the time. So this is another like project led by Mingxi. He's not here. But the general idea is just do behavioral cloning instead of reinforcement learning. Because reinforcement learning sometimes like take a lot of time for defining the reward function or reset function in the real world. That's somehow annoying, and we just want to see whether we can just directly do Equivariant behavioral cloning and then achieve a similar performance. And we also had like a method for augmenting data, but that's not very relevant, so I will just skip it. And then we again get very good performance in the behavioral cloning method. And then one demo for drawer opening. Yeah, we actually did the drawer opening in the real world, and it worked out pretty good. And then the shoe packing is actually pretty hard because you need to do 2 consecutive pick and place actions, so it's pretty challenging. All right.
I remember complaining about the shoe packing.
Yeah, it doesn't look like a real task to you.
Well, it just felt like if you're gonna pack shoes, it's like, what is the natural place to pack shoes?
Yeah, we wanted to have a shoe rack there, but I forgot why we didn't have it. I guess it's just the workspace a little bit small to place an actual shoe rack there, but we can try to do it using the UR10 arm, which is like a bigger one. Okay, it's fine. Yeah. All right, so I want to talk about the next topic. So Equivariant learning in spatial action space. So recall that before all of the works were in the continuous control, right? So we were controlling the delta action of the manufacturer. So here for the spatial action space, we will actually be controlling the target pose of the manufacturer. So we normally will have a network that takes input of the scene image in some form, and then the network will tell the agent or tell the robot where to place the gripper and what to do after you reach that desired position. So in this example, I'm trying to do a box palletizing task where I want to pallet the box on top of the rack, and then the network tells the robot to go there and then do a pick. That's like the spatial action space. So compared to the continuous control, the advantage of spatial action space is that like the action is more expressive. So at one time step, you can do more stuff than the continuous control. But the downside of it is that it doesn't have the ability to recover. So imagine like you want to reach the block, but you knock something down along the way. The agent will not know. It will still finish the desired action. But in the closed loop control, it can kind of quickly see the feedback of the delta motion and then try to fix its own error. So there are pros and cons for different methods, and they can be applied in different scenarios.
Is the potential so like earlier we were talking about how even with like a thing like move the gripper arm to the left.
Yeah.
Universal robotics software still needs to be counted on to actually like figure out
Yeah.
the motor.
Yeah.
controls.
Yeah.
So here you're relying even more
Right,
on the
exactly.
software.
Yeah.
And is that a con? Like, or is the software just perfect?
That is indeed let me see.
Maybe it's a
it's hard to say. Right. It's hard to say because if you count on your own learning algorithm, you're actually like asking it to do more. Like you're asking it to learn. We call it motion planning. Like how you should move your joint to reach the goal. You're counting on your algorithm to learn that. But sometimes we may just be able to use those already very mature algorithms for solve those motion planning for us. Yeah, I think it's a little bit hard to say whether it's a good thing or not. Yeah. So in this action space formulation, we also have some equivariance. So for example, here,
it's a scene.
oh, what? Wait, what? Why do I have? 1 second. That's a mistake in my slide. I didn't mute my video. It's good that I found out this. Otherwise, I will be like very awkward when I was doing some presentation. Okay, let me see if I fix this here. Okay, should be good. All right. So our goal here is to pick up the block, and it's actually gonna be SC2 equivariant. If we have SC2 action on the objects, we should apply SC2 transformation for our action accordingly. So again, we can define this kind of problem in spatial action space as an SC2 environment MDP, the group environment MDP that we introduced before, right? So we are in state S, we are taking action A. So the top left of the image is like, for example, you can think of the observation, like a top-down image of the entire scene. And then you rotate the state where you apply SC2 transformation to the state, and then you apply same SC2 transformation to the action. You end up with the same next state but rotated or transformed. Similarly as before, we can write down the environment property SC2 environment property in the transition function. We can write down the SC2 environment property in the reward function, and then we can try to use similar methods to solve this task. But this time it's a little bit different, right? Because recall that in the SC2 or in a group environment MDP, the optimal Q function is group environment, right? So that means if we apply the same transformation to the state action, the output Q value will not change. But normally when we are solving a problem in the spatial action space, we will be using Q learning, like we will be modeling the Q function as a function that takes in a state and generates the reward for all of the possible actions. So if we have the Q network, that's gonna change the environment property of our Q function into an equivariant property in the Q network, because we kind of move part of our input to the output side. So the environment property is gonna change into an equivariant property where the group action is gonna permute our action index somehow. So how does that look like exactly? I will give an example in the next slide. So let's imagine that we are in a state where there's a yellow block, and then we have a Q network that generates the Q value for executing all of the possible actions in our action space. So the action space here is going to be all of the possible XY position on the tabletop, which is represented in the image, and also for different type of orientations of the paper. So the first channel output is gonna be like placing the gripper like this, and then the second channel is gonna be placing the gripper 90-degree rotated compared to the first one. As similar goes to the other two. Like we just have 0 degree, 90 degree, 180 degree, and 270-degree gripper rotation for those 4 different output maps. And then each pixel in the Q map represents the quality of taking a picking action at that particular XY location and the orientation that's labeled above. So now let's imagine there is a rotation applied to the input state. So first, what should happen is that all of the Q maps should be rotated accordingly, right? Because the pixels represents where we want to place our gripper. So when the object or when the table is rotated, we want all of our Q maps to rotate to represent that change of XY position. And then this is not all, right? Because what was originally 0 degree in the original image now becomes 90-degree gripper rotation in the rotated image. And what was 90 degree before now becomes 180 degree in the rotated scene, and so on and so forth. So that means the Q maps should perform a circular shift. And this is the desired output of our equivariant Q network. So I think you might think this is very familiar, right? This is just what we call the lifting operation, or a standard, or a regular representation of the group, for example, C4. So indeed, that's what we did in the implementation. So we will first model the Q network using a FCN, fully convolutional network. So we learned from the first lecture that convolutional layers are translational equivariant. So a fully convolutional network that's like end-to-end convolutional layers. There's no linear layer or MLP at all. So this kind of network, we can think of it as approximately translation equivariant all the way, right? So we already have the translationally equivariant, so we need to include the rotational equivariance in the network. So the way we did it is we use steerable thin-in by encoding the output of the network as a regular representation. So this is good, but one of the downside of such a architecture is that in the example, I showed like 4 different gripper rotations, right? But in practice, we might want more. For example, we might want 16 or 32 gripper rotations. And then we will need to use the group C16 or C32. That's a very large group, especially if you are using steerable thin-in. It's gonna make the entire network very big. So we get around with that by decomposing the action selection into 2 steps. So before, we have a giant network that selects X, Y, theta at the same time. But here, we will first select the translation, XY translation. That's represented here. So we have a Q1 network that generates the quality for all of the XY translations. And then after we take the argmax from here, we will crop the input image and send the cropped image to the second network Q2 to generate the quality for all of the possible orientations. So in this framework, Q1 can be encoded using a smaller group, and only Q2 need to be encoded in, for example, C16 or C32. So that reduces the network size and then gonna make it learn better. So this is actually from one of my prior work back in 2020. And then in this equivariant version, we basically just, as I said, just make the Q1 and Q2 network equivariant. Yeah, any questions so far for this framework? Cool. So we tested like this framework in a lot of different environments. So those are more challenging environments than before, because in the spatial action space, each action step is actually, a long way that finish a pick or place. So, we can actually finish harder tasks within the same or similar amount of transitions than the continuous control. So the first task is house building, where the robot need to build a house-like structure as it's shown on the top left of the figure. And the second one is COVID test. I don't know if you guys remember when we had to do COVID test in the COVID center, right? Like at the beginning, there were like a system that's done in front of the table. and then there will be like 3 of us stand in 3 different spots, right? And then that people will give us the swab and the tube for us to do the COVID test. So in the second one, I'm trying to mimic what the assistant is doing, like basically replacing him or her with a robot. Just presents 3 tubes and swabs to a user and then collect the used ones. It's very timing because the paper was published in 2021. That's where we need to do a lot of COVID. Good that we don't need to do it.
You built that sim?
Oh no, Xu did that.
Xu did that?
Yeah, Xu did that. And then the third one is the box palletizing. This is actually the most challenging one because there are 18 boxes, and then the robot need to stack them one by one. So this actually gonna be 32 time steps to finish the task. And then we have bin packing, where the robot need to compactly pack all of the random objects to a bin. So here on the we again show the learning curves. The x-axis is the number of episodes. Recall that this is not the same as number of training steps as I showed before. The number 1 episode can contain several training steps because, for example, for this task, 1 episode is at least 36 time steps. For different tasks, the episode might be different, but the x-axis here is the number of episodes, and then the y-axis is the reward for the episode. So here, we again outperform all of the baselines. Yeah, including like a state-of-the-art behavioral cloning baseline, transporter network in RAC. But anyway, we just did better than all of the baselines. Okay. Yeah, so comparing the blue line with the green line, the only change we make is replacing the network with an Equivariant network. So that that shows like how powerful geometric machine learning can be in actual tasks. Okay, so this is great. And then in the following project led by Xu, we actually did real world learning again for grasping. So this time is similar as what I did before in the continuous control, but here it's more challenging because first we have more objects in the bin, and second, those objects are more like rigid. So in the previous slide or in the previous method, like objects are actually soft. So there are a lot of like you can squeeze it so that you can pick it up, but those rigid objects you cannot really squeeze it too hard. So here on the left I show the learning curve again, and on the right I'm showing the evaluation policy after training. So this is only trained for 1.5 hours, and then you can see like the resulting policy can be very robust. So this is testing in unseen objects. So none of the objects are seen during training, but it can very robustly pick up all of them. And in the left, the learning curve shows the number of graphs versus the success rate for the previous 60 graphs. So you can see after 600 graphs, our method can reach like 92-93% success rate, and it's much better than the competing baseline. So during testing, we actually got higher success rate because during training, we actually have some randomness in the policy so that you can maintain some kind of acceleration. You don't want to overfitting to your current policy. You want to try to explore some new graphs. So during testing, we can do like a better than that.
Is this the one you took to Philadelphia?
Yeah. So last year we took the robot to Philadelphia to show a demo in ICRA, International Conference on Robotics and Automation. That was a fun trip. So actually, it's a lot of stuff to take over to Philadelphia because the robot computer. We're glad that it really worked out. So if we forgot one cable, we can the whole trip can be wasted. But yeah, I'm very happy that it worked out. Okay, so I might skip this one. This is another work led by Hao Jie in our lab. So basically, we there's a very powerful architecture for solving pick-and-place tasks in robotics, and then if maybe the author didn't think about it too much, but in its own implementation, it actually is using the lifting operations to implement some kind of algorithms. And then we but there are other components in his or in his framework that's not equivalent, and then we basically make all of them equivalent in our version, and then wait what? Oh, okay. So animation is really well. Okay, so we make all of the networks equivalent in this framework, and then we show a great improvements than his original one. So here we have some fancy environments that we are trying to solve. I'm not going into detail of them, but what I want to show is that sometimes we can learn better than the baseline with like 100 times less data or even 1,000 times less data. So here, our method trained with 10 demonstration is better than what they trained with 1,000 demonstration. And here we can do better with just one demonstration than what they did with 1,000 demonstration. So I think this is a great improvement.
Except for Lawson, if you're one demo.
Yeah, that's also one demo. Yeah, and then Haojie also led another project to apply SE3 equivariant in grasping. So if you think about grasping, right? So here, the yellow thing is the gripper, and then we have an object which might be a bottle. So what we were considering before were mostly in-plane orientation or in-plane translations, like SE2 transformations. But the grasping can actually be SE3 equivalent. So you can just rotate it or reflect it whatever you want, and then you should still have your gripper transform accordingly. So I'm not going into detail of this, but using SE3 equivariant architecture, the vector neuron, I think you might already know it. We can.
I don't think we talked about it.
Oh, you don't have it? Okay. It's just a SE3 equivariant neural network architecture that takes input of point cloud. So our method is just much better than the baselines without considering equivariance in the network architecture. Okay, so I want to talk about save some time to talk about the next topic, which is handling latent symmetry. So we all know that equivariant networks are great, right? So this is an example of an application of equivariant network. We can also think about the robotic examples that was shown before. So here, we want to estimate the position of the duck, and then the output should just rotate when the state rotates, right? So we can try to use equivariant network to encode that property, and then we can greatly improve sample efficiency and generalization. You already showed that.
What's the output here?
The output is two vectors. It's the x-y position of the duck.
Oh, okay. It's not the direction the duck's facing. It's like
no,
where it is
no.
relative to the sun.
Yeah, right. Okay. But one of the main constraint of using equivariant networks in the image space is that we will need a top-down image, right? Only when we have a top-down image we can represent the rotation of the state using the rotation of the image. But in the real world, we might not always have access to a perfect top-down image. There might be some fixed background that will not rotate as the image, or even we have a set view camera, for example, 45-degree view camera instead of the top-down camera. So this is very common in the real-world tasks. So for example, in robotics, the ideal top-down camera might only exist in the simulator. So in the real world, because of the occlusion of the arm, maybe we don't have access to a perfect top-down camera, or we need a significant amount of pre-processing to generate that kind of top-down image. That's what I did in my previous projects. On the right, there's an example of jet flow data. So there could be some flipped environments in the data, but we can see there are a lot of noises in the data that might break that equivariance. So under such a scenario, they will. Yes, please.
Can you go back to the what is the goal there with the fluid example?
I mean,
Sorry, it's just the GIF on the
yeah. What is the goal?
The fluid, the jet flow.
Is it prediction? Prediction the flow? Sorry,
Oh yeah, usually you're well, you could imagine different. This is just some data from NASA. So you could imagine like just trying to predict the future flow. As an example.
Yeah.
Like, okay. Or you could try to classify some properties of the flow. But the standard task would be predictive.
And you're saying like the black dots, that noise breaks equivariance.
Yeah.
Not like the overall chaotic nature of the flow.
Yeah, the chaos should probably be pretty balanced, but like the one thing that was neat about this data is almost all like machine learning for fluids is trained on simulator data. There's no like noise, but actually like here there's actually like they actually like used like a bunch of like cameras and tried to like reconstruct the flow, but like there's bias in the cameras, right? They don't represent the symmetry of the underlying differential equations perfectly. So the data you're training on is perfectly symmetric.
Okay, so when we have this kind of scenario, like for example, fixed background where we have a side view camera, there will be a mismatch between the problem symmetry and what we can model using an equivariant model. Sorry, and what the symmetry we have in a model when we are using equivariant model. So for example, like here, if we use the steerable thing again to enforce the SO2 rotation equivariance, right? So the actual object transform or the actual problem symmetry is the rotation of the objects. But what we can enforce using an equivariant network is the rotation of the image. So there's a mismatch between those two things. So when that's the case, we cannot find a perfect equivariant network to model the object-wise symmetry. Because we don't know what the input representation is. It's hard to write down the rotation of the dot in a side view image using some equations. But what we can still do is to use an equivariant network that's equivariant to image transformations. So in this work, we found out that even though in this scenario there is a mismatch between our model symmetry and the problem symmetry, the equivariant network can still be very helpful. It can help a model to better learn the object transformations. So we will call this approach extrinsic equivariance. So it is extrinsic because if you think about the rotated images, those rotated images will be out of the input distribution. So you will never see a rotated image during training or testing. So we are enforcing equivariance towards out of distribution data. So that's why we call it extrinsic equivariance.
Why is it out of distribution?
It is out of distribution because in your task, the camera is always 45-degree viewing the workspace. So like
I see.
Yeah.
The camera's fixed.
Yeah.
All your data was collected.
Yeah, from the same camera. Okay, so so in this work, which I'm gonna present in Rwanda soon. So we make two contributions. So the first one is we define 3 different relationships between the problem symmetry and the model symmetry, and we call them correct, incorrect, and extrinsic equivariance. So correct equivariance is when the model symmetry matches the problem symmetry. Incorrect equivariance is when the model symmetry conflicts with the model symmetry, with the problem symmetry. And extrinsic equivariance is when the model symmetry will transform the data to out of distribution. So I'm going to introduce them in the following slides about like what they exactly mean. So we also show that incorrect equivariance will lead to some inevitable error because you are making your network, you are forcing your network to generate some wrong answers. But extrinsic equivariance can actually be very helpful. So I will introduce the concepts using a binary classification task. So here, our goal is to classify the blue and orange data, leaving on R2. This is the XY thing. And then we want to find a hyperplane that separates those data. So the green region is the data distribution. So let's consider there's some structure of the data where the data distribution forms a ring, right? So now the green region is only the ring here. So since there's some structure of the data, we can consider using some, equivariant architectures to better solve the task. So let's first imagine an equivariant network that's invariant to vertical flip. So here I'm showing the group transform data under vertical flip using crosses. And then the circles are the original data. So if we compare the crosses and the circles, we can see that their colors perfectly match. So that means the symmetry in our model agrees with the symmetry in the data. And then we call this correct equivariance. So in fact, this is also like the normal case when we were using equivariant networks, right? So in all of the work that was presenting before, we sort of have this correct equivariance. We find the symmetry in the model, and then we define an equivariant network that respects that kind of symmetry that we discovered.
You could pause, and it'd be a good quiz question.
Yeah.
For everybody, for like, what kind of symmetry would be incorrect?
Oh, right. That's a good point. So yeah, can someone give me like a incorrect symmetry? Like for example, what type of symmetry will be wrong for our task? Right, so it's actually
Left, right,
sorry, what's that?
left, right flips or rotations?
Yeah, exactly. Yeah, left right flips, or left right. In this case, left right flip is the same as a pi rotation, right? So an incorrect.
Well, it's not the same.
It's yeah, right, exactly. It's not the same. It's similar. Yeah, because when you flip, you are mapping those two together. But if you are doing pi rotation, you map those two together. But in the end, like you end up with the same blob. Yeah. So here, if we consider pi rotation invariance or horizontal flip as sorry, I forgot the name of
Nicholas?
Oh yeah, Nicholas. Yeah, sorry about that. Yeah, as Nicholas was talking about, we will see that the group transform data under pi rotation or under horizontal reflection will be different from what we have in the original data set. So that means like the model symmetry is actually conflicting with our data. So in that case, if we use a network that's invariant to pi rotation, we can actually get up to 50% success rate because the network is gonna assign the same label for the pi rotated data pairs. For example, like this one and that one, the network will say, okay, so those two should be invariant and they should have the same label. But in the ground truth function, they have different labels, and that happens for the entire domain, and then you can only get up to 50% success rate. And this is bad. So we know this is bad. We don't want that. And then we also know the correct is good. We want correct. But there's actually a third scenario that's kind of in between correct and incorrect. So what if we enforce scaling invariance? So under scaling, the group transform data will be outside of the input distribution as it's shown in the gray ring. So in this case, even though the symmetry in our model does not match the symmetry in our problem, it's not gonna lead to any error, right? Because the group transform data is out of distribution, and then we are not like forcing a network to generate any wrong answers. It's just like kind of enforcing a relevant symmetry. So this is not bad, but we actually found out this can be good because this kind of extrinsic or out of distribution invariance can actually make it easier for a network to generate the decision boundary. So this is our hypothesis. Yes.
So like, would this be like, for example, if I did a rotationally equivariant network on MNIST?
Yeah.
That extrinsic?
Yeah. If you yes, I think so. Well, it's gonna be some combination of correct, incorrect, and actually.
How about like image?
Yeah. Well, when we MNIST, we think about number two.
Okay.
The two is gonna be extrinsic because no matter how you rotate the two, there's no digit that likes two.
Okay.
But if you think about 6 and 9, right? So you rotate 6, you get 9, and you reflect, you flip 2, you get 5.
Okay.
Yeah. So I think it's kind of like a combination. Yeah. And for ImageNet, I think it's a little bit hard to say, but I agree that it's gonna be mostly extrinsic. Yes.
Right. Like I don't know, what are the classes?
I don't know. I know.
Car,
Yeah.
Table.
Mhm.
There'll be like probably not very many upside down pictures of tables or whatever. So it's like,
Yeah. Okay. So this is we call this extrinsic equivariance. And if you look back to our image example, right? So we have a set view image, and there's some object in the image. So all of the object rotations will be in distribution. It's in the gray region. But if we rotate the images, it's going to be out of distribution, right? Because all of the rotated images, we will never see them during training or testing. So if we use a rotational equivariant network to process those side view images, we will have extrinsic equivariance. So to validate, this extrinsic equivariance is helpful, we did some experiments. So the first one is a supervised learning experiment. So here, the network will take in two images, and then the objects in the two images will have some kind of rotation. And then the network need to estimate the relative rotation between the objects in the two images. In this example, the three dots are rotated clockwise by 3/4, and then the network should just output 3/4. So this task is an invariant task because if you rotate both of those two images, the relative rotation will not change. So this can be implemented using a rotational invariant network.
Already a good response.
Oh, yeah. Okay, so if we have a perfect top-down image, we will have, the so-called correct equivariance, right? But we can also introduce some symmetry breaking factors that will lead to extrinsic equivariance. So for example, we can include a grid that will not rotate, and then you have extrinsic, or like we have the side view image, and then you have extrinsic. And then under each of the symmetry corruptions, we compare the performance of an extrinsic equivariant network versus an unconstrained CN network. So here in the plot, the blue line is the extrinsic equivariant network, and then the green line is the unconstrained network. The x-axis is the number of training data in the training set, and the y-axis is the test accuracy after convergence. So we can see that in almost all of the cases, the blue is outperforming the green. So that means like even the symmetry in the network is extrinsic, it's still like helpful compared to a network with no constraint at all. And another trend we can see is that when we have more data, the gap between the extrinsic equivariant network and unconstrained CN is smaller, and that's I think normally when we have when we use equivariant networks in machine learning, we will also see that because that equivariant network is more sample efficient, and then you give more samples, the CN can eventually catch up with the performance. So we also compare a data augmentation baseline in red. So the red line is just the green line, but equipped with rotational data augmentation. So the red line is also achieving equivariance, but it's doing that through data augmentation instead of doing weight tying. And we see that the right line have a very similar performance as the blue line, and that means we kind of prove experimentally that extrinsic equivariance is helpful through two different approaches of achieving equivariance. And the second experiment we did is in robotics. So the similar experiment that I was showing before, but instead of making that top-down image, this time I would just use a side view image directly. Like we have a camera that's looking at the workspace of the robot from a 35-degree angle. So here I was using the equivariant stack algorithm, the first algorithm that I introduced in the talk. But with the non-top-down camera, and that non-top-down camera is gonna make its equivariance extrinsic. And I compare with like similar baselines that I did before. So this time, like the gap between those two methods are smaller, but it's still pretty significant. Like we can still be better than the baselines. So notice that here, the baselines are doing better than what I showed before, because here we actually use more demonstrations, because it's with a side view image without the correct equivariance is it's a harder task for all of the methods. And if without more demonstrations, our method can actually not solve it also. So we just included more demonstration here. Yeah, so the blue line is our method, other colors are the baselines, and then we outperform significantly. Okay, so to sum up, I think recently in the lab, by collaborating with Robin, so we did a lot of works in using equivariant model in robotics. So we defined grouping around MDP, and we had different applications of grouping around MDP in both continuous control and spatial action space. And we also explored a little bit in how to handle latent equivariance, which is a very common scenario in robotics. And then for future work, one of the things I want to explore is that right now, most of my works are limited in a subgroup of E2 symmetries. I was mostly focusing on in-plane rotation, translation, reflection. In the future, I want to kind of like explore different symmetries. I think robotic tasks are more complicated than just planar symmetries. There will be like, for example, IC3 symmetry that I can explore. There might be local symmetry instead of global symmetry, or permutation symmetry of objects, a lot of different stuff that we can explore. And also, we might want to find better ways of handling latent equivariance, like the last part of the talk. So that method is good, but maybe there are better ways of handling that, or maybe we can provide a theoretical explanation of it, because right now we only demonstrated experimentally that it's helpful. We don't really know, or we have some intuition, but we don't have very theoretical explanation.
I guess if you publish a paper with a title that includes the word surprising, it's a good indication that you have more work to do.
Yeah. We need to, that means like there will be a second paper titled explainable or something. All right, so I want to thank all of the co-authors of the works. Some of them are here, and then some of them are in the lab. None of the work is really possible without their hard work. And then there's a paper list of some relevant papers that I have been talking in this lecture, and also some ones that I didn't have time to talk about. Also, like there's a QR code of, I think it's my website, maybe. Yeah, you can find our works by scanning it if you're interested. Yeah, I think that's all. In the end, I'm glad that we are actually hosting a workshop on symmetries in robot learning in the top robotic conference, RSS 23. So it's gonna happen in July 10th at Daegu, Korea. We have some incredible speakers. We invited some of the geometric machine learning people like Pat Smith. It's very good that we will be hearing from their side on how can we better leverage symmetries in robot learning. I think this is a great robot learning. I think it's a great area for applying equivariant models, because it's very natural that in robotics we are executing stuff in the real world, and there's some very natural geometric structure, and it should be somehow use the method we have been learning in the course to better handle those problems. Yeah, that'll be all. Thanks a lot, everyone.